Yeah, you can share and go ahead.
So yeah, I'll start sharing screen. So continuing from last time, I just wanted to, before I go into the code, I just wanted to give sort of an overall pseudocode level overview of the entire training process. Okay, one second, I need to connect the tablet. Yeah. So this is a pseudocode level overview of the training process. So basically, if you remember from last time, the basic essence of the basic workflow of the gradient descent algorithm was something like this, right? So you have some neural network and you have decided on some using some loss function. You have some training data and you're going to train for some number of steps. Then what you do essentially is, after all the initialization is done, you just iterate over the number of steps that you have, and at each point, like for each step, you calculate the gradient somehow, and then you use that gradient to somehow update your parameters.
So
Now,
what does init_ran do? It just picks some initial value for all the weights.
yeah. So it just randomly initializes the weights.
Yeah.
So now, so essentially, if you look at these two functions, these two functions, how they work internally. Getgrad, what it will do is it will basically for your particular given loss, it will calculate the gradient and return it. So that again, exactly how the gradient calculated is depends on the loss that you're using. If we, for example, use the mean square error loss, right, then the gradient calculation essentially looks like this. You take the y and the output of the network, subtract them, and then multiply it with the gradient of the output of the network. So this again needs to be calculated, and that is what AutoGrad would handle. So in general, what we would do when we are writing code in PyTorch is we would just let AutoGrad handle this entire function. So this entire getGrad we won't need to write it explicitly. This entire thing is going to be handled by AutoGrad, right? So AutoGrad would also basically automatically do this part for us. Is essentially what I'm saying. This summation and multiplying the part and all of that. So the other sort of black box that we'll use is this optim step function. So if we look at the particular function that we have here, the simplest case is just that, the optim step, what it should do is essentially to take the gradient, it should take the current parameter value and give you the parameter value for the next step. The simplest way would just be to, take your current parameter value and then just add gradient times learning rate. Actually, they should be subtract technically. So I should maybe say minus over here. So let's put a minus over here. Yeah, so basically it should just go along the opposite side of the gradient. So it should just take the gradient multiplying learning rate and add it to the parameters, right? But as I said, that there are some more complicated ways you can do this. Like there are more sophisticated optimization algorithms which don't just do this. They change the learning rate according to whether you're close to the minimum or not, and sometimes they add something extra or use some momentum to basically make this training process converge faster. So that entire thing again is going to be handled by an optimizer. So this entire function, when we use PyTorch, is going to be handled via an optimizer. And PyTorch gives us a list, like a huge list of optimizers to select from. The one which we will be using, and again, I think in my experience, this works sort of the best in most cases, is this Atom. It will just be using Atom with all the default knobs, but there is a huge choice of optimizer, and each optimizer has got a several sets of knobs. And if you want to, you can go in and read the documentation as to what they are exactly, and you can use that to sort of tweak them. But usually this works, and usually tweaking is just some trial and error. So yeah. So finally, this is the normal gradient descent. What we'll be doing is actually SGD, so stochastic gradient descent here, right? So SGD.
Hello? You guys there?
Yeah, but I think Diganta got disconnected or something.
Could be. Let's see, but Diganta is still there on the. Let me call him. Yeah. I think he'll rejoin. So. Yeah, he got disconnected. So I presume he'll join. Let's wait. Maybe there was a power cut or something. No, he's back. Diganta, can you hear us? Can you hear me? Some problem.
Can everyone hear me?
Yeah. Okay. Yes. Now I can hear you.
Yeah. Sure. Share screen.
Yes, I made you progress. Yeah.
Yeah. So okay, yeah. So what we'll be doing is SGD, which with the difference is basically we're going to split the data into multiple batches, and instead of calculating the gradient with respect to the loss for the entire batch, we're going to calculate it, or for the entire data set, we're going to calculate it for each batch. So notice that when we go from this to this, none of these, like these two functions don't need to change, right? So these two functions essentially remain the same function. It is just that we structure our outer loop differently. So with PyTorch, what you would essentially need to write is just this outer loop. As I was saying, these two functions are already taken care of by the library itself. So if there are no questions, then I'm just going to go into the code and show you guys how things work in PyTorch.
Any questions?
Okay. So
Okay.
I'll just go ahead. Yeah. Um, right. So can you guys see?
I can. How
Could
about
you zoom in a bit if possible?
Right.
The
Yeah. Is this okay?
yeah.
So yeah. So firstly, let's import torch. The first thing I want to show you is the how the autograd feature works, right? So for that, let's create two tensors. Okay, so is everybody familiar with NumPy and tensors and so on? Is there anyone who's not familiar? Give me a yes or no. Are you familiar with NumPy and how it handles tensors?
anybody
I'm
not
familiar
familiar?
with NumPy, but not that much with tensors. Like if you could just go over it a bit, I guess.
Yeah, sure. So I mean, we don't need to like this is not with respect to the mathematical concepts of tensors. So uh, yeah, so you don't need to really understand like from a rigorous mathematical point of view what a tensor is and so on. If you're familiar with NumPy, you know that like in NumPy there are arrays, right?
Yeah.
So how would you create an array in NumPy? You'd go something like x.np.array and then something here, right? So you do something like this, right? So this in both in TensorFlow and in PyTorch, this arrays of like 1, 2, 3, or how many ever dimensions that you have are called tensors. So
Okay.
yeah, so there is a mathematical reasons for that, and there's a very rigorous definition of what a tensor is, but I'm not going to go into that right now. If that's okay. Like you can look that up, I guess. But essentially, you can think of tensors as being multidimensional arrays, and
Okay.
yeah,
Yeah.
and the normal things that you would do with such arrays in NumPy, you can do it in PyTorch and TensorFlow. So all of your usual, multiplication, dot product, how things are being broadcasted, all of those things carry over here fairly similarly. Like in fact, they're mostly identical. So, so if you know NumPy, then just know that whenever I'm saying tensor, I mean array, and everything else is the same. So is that okay for everyone? Is there anyone who's not at all familiar with NumPy as well? Okay, so everyone is familiar with NumPy. So
What have you used it for? I'm curious. NumPy.
Oh, so I have done multiple internships in which I had to use it. So I am very familiar with the.
Okay, this is Devjit.
No, this is Amir.
Yeah.
Amir. Oh, okay.
Yeah.
The other two have used in what context? I'm just curious. That's all.
Coding DNNs. So I am
You
familiar
have.
with how
Oh,
to
okay.
code DNNs.
What do you mean code DNN? So this is what?
As in people use TensorFlow or PyTorch APIs. So people don't really code DNNs completely. There are like a lot of libraries, and you build on top of those libraries. And one of those libraries is PyTorch, which Diganta is doing right now. Another is TensorFlow.
So you have used it to actually train some real neural networks.
Yes. Yeah.
Okay. So this is Harsh, is it?
No, Devjit.
Devjit. How about Harsh? Is Harsh here still?
Yes, sir. Yeah.
No, I'm asking the same question to you. So
Okay.
the context in which you have used NumPy and how familiar you are with the training part in constructing DNN and so on.
So like I have used NumPy and TensorFlow. Like so, TensorFlow load like by just like whatever the API kind of thing is, like load neural network, and that NumPy I have idea, like I can multiply matrices and stuff and look up the API if I have some doubt.
So in what context where did you learn DNN and so on? So you did it for a course, or did you do it as a hobby?
Like as a hobby, I have been doing for a long time, but in some other language. And last year, I think I did an internship in which like I implemented neural networks for stock market stuff.
Internship where? Some company, is it?
Release technologies.
Ah, okay. So you guys are somewhat familiar. Okay,
Yes.
good. Yeah.
Okay. So yeah, so then yeah, I'll not go over any of the usual NumPy things, but let's just. So I guess so. Also, I would like to know that between PyTorch and TensorFlow, what are you guys more familiar with? Like, Devjit, have you used PyTorch or TensorFlow? Which one did you use usually, or have you used both?
I have used both actually. So.
Yeah. So yeah, and Harsh.
I've used a little bit of both, but not a lot. Not
Okay.
just the basics of both, but yeah, both.
Right. And Harsh.
I've used TensorFlow, but I have heard that PyTorch is better. Like, I don't know.
Yeah. So okay, so I've used both, but more of PyTorch than TensorFlow, far much more of PyTorch, and yeah, I've also heard the same thing, and from what little comparison I've get, I also felt that PyTorch is arranged in a better way, let's say. But in any case,
what is the advantage? What is superior about better?
So it's because it lets you do things in a more functional way, let's say. And that allows you to, when you go into more complicated code, that will give you a lot more freedom as to how you arrange your like say for RNNs and LSTMs and things like that. You can make a lot of changes to the code. You can arrange your code in your particular way. So all you need to do is define what the forward direction of your DNN or whatever model you are training needs to be, and the rest is all managed. So that is also the case with TensorFlow, but it is becoming more functional, I think. But traditionally, it was a little more rigid in the way that they had laid it out, and you could only
So
use.
now TensorFlow has this thing called dynamical computational graphs, which is how PyTorch is also built. So
Yeah,
they're almost same now. Yeah.
right. But I guess the sort of TensorFlow I worked with was fairly an old style, which felt a lot more rigid than what PyTorch feels like.
Now, in terms of the input DNN net format, is there a standard thing that both use? What is the input format if you want to?
So if you're looking for a file format, something like the .NET thing that say Marabu takes in,
Okay,
that is not like I don't think there is any format that works for both of them.
so each of them uses its own
file
format.
Right. And what usually people, when they're specifying what kind of a neural net they want, so usually the architecture is specified in code, and when you get weights, then people usually just save in whatever their own formats are. So yeah. If you wanted to say go from one, so if you had the model in TensorFlow which you've trained, and if you wanted to write it in PyTorch, then I think you'll have to basically do some manual copying. Like by manual, I mean read it in using TensorFlow. Then
Yeah, see, this is something that we'll have to. Although we will be requiring them to use only NumPy and the thing. So that thing. So, but since they will be training, possibly, I mean, definitely training for the project, or maybe using existing network, and certainly whatever that they build on their own or that we provide, they'll certainly be have to input to the verification tools.
Right.
This formatting is something that we need.
Yeah. I don't think there's any easy way to get around it except for just if we train something, or if they have to train something, let's just all agree to use one particular thing. Which I mean, I have already started doing something in PyTorch. So
okay.
So if that could be one way, but I think other than that, like it'll just require people to write some format handling code, which is not too difficult. But yeah, I mean, we can also do that if it turns out to be too tangential to what.
Okay, so we'll cross the bridge when we.
When we get there, I think. So okay, so I think then if most people are familiar with PyTorch, this things will be fairly already known to you. So I'll not spend as much time as I was thinking I would to. But
yeah, but if there are any specific questions that you have, I mean, or you can even add things, okay, based on what your experiences and so on, please feel free. So you just go as per your plan, Diganta. Okay, so whatever that you wanted to cover, you cover.
Yeah, sure. Okay, sure.
Ask questions and make comments.
Do like tell me like stop and say things basically essentially. So okay, so let's do something. So let's create two tensors in PyTorch and let's see how the autograd function works first. So and then we can just have say two, or let's just keep it a single like a vector. So say 2, 3. So yeah, so as you can see, it's a tensor with 2 and 3. And notice some things in Python, there is no difference between ints and floats. Like everything is just as in there is an internal difference, but usually there is no idea of specifying data type. So since you're passing a Python list to this tensor, there is also no idea of like specifying a data type here. But of course, similar to how it works in NumPy, usually it's interpreted as floats. So if you want a tensor of integers for some reason, then you have to specify some extra data type parameters here. You could say something like, and you could say, I think it's called d type, and you can say d type int if I'm not getting the domains wrong. So you can do something like that if you want a tensor of integers, but usually it's a tensor of float, which is why you get the dots here. So let's have another one. So let's say y is right. And now let's say that we'll have this. So we'll say that z is going to be dot product of right. This is 23, which is correct, right? So 2 times 4 is 8 and 15 is 23. So now what we're going to do is, okay, so how PyTorch's autograd works is essentially each tensor has this extra field. So if you look at all the things inside a tensor, then you'll find this extra field which is corresponding to a gradient. So
what is this dir command?
Oh, so this dir in Python, if you do dir of any object, it give you all the members of that object, including variables and functions and all of everything. Yeah. So I'm just going to do essentially a search, and I'm going to look for things with grad. So you're going to see that you have this particular field here, right? So essentially for x, there is this thing called x.grad, and right now it's none. So it's not printing out as anything. So if you see, look at the type of x.grad, right? So it's not none type. Underscore grad, I think, would be 0. No, it's also none. Okay. So essentially each tensor that you have, so remember what we now have 3 tensors x, y, z. Each one of them has this field called grad, right? So initially all of them are none, and none you can sort of interpret it as 0 as well. Whenever you do some calculations, so right now the calculation that we have done is x is the dot product of z is the dot product of x and y. So whenever you do some calculations, what happens is that internally this compute graph that we were talking about last time, right? So we had this sort of graph of things that showed us how things are being computed. So this compute graph internally gets basically constructed every time you do some calculation. So right now we have done z is dot of x and y. So that is being internally encoded as a part of this compute graph. And usually if you want to actually inspect as where that is happening, that is usually happening in some, if I remember correctly, there are these backward functions that are also fields of the tensors that register what function this tensor was generated using and what were the inputs and so on. So what you need to understand is that right now Z has the information, or there is some information in PyTorch which is storing the fact that Z was computed using the dot product of X and Y. And what you can do now is you can do Z dot backwards. So I think it's called backward. Oh, okay. So yeah, I think we forgot to turn on the required grads parameters. So let's do that. And so required grad will actually turn on the fact that these things need to track the gradients. So if you so usually when you're working inside working with PyTorch, depending on what context you're creating and computing these tensors in, PyTorch decides to either turn on this entire mechanism which keeps tracks of the gradients and creates this compute graph, or keeps it turned off. So by default in the CLI or in the Python in like interactive mode, you don't have the required grad parameters turned on, which means that the gradients and the compute graph is not being created automatically. So if we turn this on, and let's do the same with Z. There we can do this again, and now if we do this, okay, why is it still?
I think it requires grad, right? According to the not require.
Oh, sorry. Yeah. So yeah, now if you do x.grad, why is it? Yes, yeah, so Z's gradient is being computed as being 1, so that's fine. Why is X's gradient not being computed? Okay. Does anyone have any idea why this is happening?
It's not tuning.
I mean, I would guess that you're only changing Z. That's why the Z.
No, but if you do Z dot backwards, then it should go back along the entire compute graph, right?
Yeah. What does backward do exactly?
Yeah. So backward would basically start this backpropagation algorithm that we talked about. So remember, what backpropagation did was that it assumed that you have these edges are labeled with the intermediate values of the various functions that you have, and under that assumption, it would basically go back and calculate the gradients by labeling the edges and so on. So this entire autograd algorithm backpropagate starts. So if you call backprop.
In terms of your pseudo code that you showed, Diganta,
yeah,
what does back do? Go to your pseudo code.
Yeah, so it's not directly related to my pseudo code right now. So
okay.
I'm just trying to demonstrate something even before that, and that is not seems to.
Maybe like you have to backward every layer, right? Maybe.
No,
I don't know.
but then usually when you do loss.back.
Yeah, exactly. It just
right.
does everything.
So maybe the dot product doesn't, but that also doesn't make sense. That the dot product. Okay, sure. So let's just do this. We'll be recreating the sorry about this. Just look this up. Yeah, I thought. Okay. All right. So I think what my mistake was that this is not the particular tensor class that we want to work. It's a small t tensor. So yeah, I think that's why it did not work. And I think another reason is that the Z that was created ultimately was probably the correct tensor class, so that had its own grad. And this should now hopefully work. So it is Z to be dot of X and Y. Oh. Yeah. Right. So I hopefully have not confused you too much by these mistakes, but basically what I wanted to demonstrate is that you just need to create these tensors, make sure that a required grad is true. And usually this is also like made sure by the particular context in which you're creating this tensor. And then whatever computation you do, when you finally get to, remember that Z is coming from a dot product. So Z is essentially a zero-dimensional tensor, a scalar, right? So if you print out Z, it's going to be just a scalar, whereas note that X has got actually two elements in it. So when you do backward from a scalar, all the computations that was done to create Z, torch will automatically backpropagate along those, and for each one of the tensors involved in those computations, it will fill this dot grad parameter with the gradient of your Z with respect to this. So for example, X dot grad is going to have the gradient of basically the gradient of Z with respect to X. So this 4 means that this is the derivative of Z with respect to this particular component of X, which makes sense, right? Because what we're doing is the dot product. So that looks like this, right? So we have X1, sorry. Yeah, so we have X1, X2, let's say, and that was, if you remember, 2 and 3. Similarly, Y1, Y2 was 4 and 5, and the dot product would be X1, Y1 plus X2, Y2. So that is Z. And now if you do the gradient, X1 dot grad is going to be this particular vector. It's going to have, so this is Z. So it's going to have del Z, del X1 and del Z, del Y1. And just hopefully you can see that del Z, del X1 is in this case will be 4 and del Z, del Y1 in this case will be 5. So this is 4, 5 and that's correct. Similarly, you can check Y dot grad. Right. So just to summarize, you can basically in your code, you can do all sorts of calculations with all sorts of tensors as long as they have this required grad parameter set to true. When you finally combine them all in any particular, in using any way that is supported within PyTorch, if you use them to combine and calculate and finally get a scalar, you can do dot backward on that scalar, and that will just start autograd for you, and it will fill up the dot grad parameters of all your tensors, right? And that will have all the gradients that you're looking for. So any questions? Does this make sense?
Yeah. Like if you have Z is equal to XY, and you do Z equal to backwards, it will calculate all of the variables. Like it will go all the way back to the graph and calculate gradients for all of them, which lead up to Z.
Yeah.
Oh, okay. And so like X dot whenever you do x dot grad, it is actually the gradient of z with respect to x.
Yes, yes. Whatever the last dot backward you did. So essentially, if you do two dot backwards back to back in some sense, if I were to do some dot backward again, let's say, right? So the second time you call dot backward, the gradients will get added up. So right now, okay, so x dot grad was 4 and 5, 4,5. Okay. Right. Okay. Actually, it actually is complaining because it has already done one back propagation. So essentially,
do it again, like
yeah. You'll have to. So usually when we do this, we do a 0 grad, but I think you can disable this. Using this particular flag, and then it will add it up over and over again, if I remember correctly.
Okay.
So the idea is that when you do z dot backward, it will fill up all the tensors involved in the computation graph with the gradient of z with respect to that tensor. So it's going to fill x with respect to del z del x. X dot grad will become del z del x. So any questions? Okay. So hopefully this was like, I made a few mistakes here. This was not very confusing for people.
So each back is doing one step in that graph, is it? The function graph?
Yeah, so each time you call dot backwards, you're doing this entire process once. This entire autograd backpropagation process.
No, the whole thing from the output all the way to the input.
Yeah.
Yeah.
So notice that this actually does not require the set of calculations that you do to be of a particular NN or anything like that, right? Any calculation that is supported by PyTorch, and sometimes you can also do like you can extend PyTorch and define your own things as well in some sense. But essentially, any calculation that is supported by PyTorch, you can do a backpropagation over. So specifically, you don't need to do it just with respect to calculating the derivative of the output of the neural network. This getGrad function, this entire thing can be done directly by just calling dot backward, right? So instead of having to write a getGrad function separately, what you would need to do just is that you would need to do the forward direction of the calculations, right? So for example, if your loss is a mean square error loss, all you need to do is create a scalar tensor called L, and then do some calculations to calculate this mean square error loss, right? So you'd have to say run a loop, calculate the y minus x whole square, and you can do say sum of y minus ny whole square, comma, like y minus ny whole square for y, sorry, for x comma y in data, right? You can do something like this, and then if you do loss.l dot backwards, automatically all of this gradient calculation is being handled for you. So this is how the backpropagation essentially.
So the getGrad is actually implemented in two steps, like here.
Yes, the getGrad is essentially being implemented entirely by PyTorch itself. So what I'm trying to say is that all
you wrote two steps here. L is equal to sum and L dot backwards. Correct?
Yeah. So the first step is not calculating the gradient. The first step
I know that, but the two things put together.
Yeah, the put together will give you the gradient finally. So basically what PyTorch says that you do the forward calculation and then call dot backwards, it will do the backward calculation for you. So if you remember, in this backpropagation, we had two phases loosely, right? We had this forward calculation phase where these green values were, these black values were being calculated. And then you had the backward calculation phase where all the gradients were to be calculated, right? So what PyTorch says is that, okay, you do the forward calculation phase and then you call dot backwards and we'll do the backward calculation phase.
Which is what you've shown as getGrad here, or no?
Yeah, so the getGrad here was it's not a direct, it's not going to, you're not, what I'm trying to say is you don't have to implement it in this way. So last time I
I
talked about
I understand, but functionally, I'm saying.
yeah, functionally these two steps combined give you get
Correct.
that.
Okay.
Yeah.
Okay.
So PyTorch is like a normal library, except like it's like MATLAB, but you get gradients for free.
Yeah, you can think of it like that.
Okay.
So it's like, it's in fact, it's like you can do everything that you do with NumPy and a lot more, because you have, the loss function and so on, but you get gradients for free. So I'm not sure between MATLAB and NumPy which one you would call more powerful or anything like that, but
I mean, like NumPy, MATLAB are similar, except MATLAB is like very like it's like small notation. So
yeah, okay.
but like yeah, the idea is like you are just getting NumPy with gradients for free.
Yeah, exactly. That's
Much
exactly
more elegant. I can't even remember the TensorFlow API. This is like way better.
Yeah, which is I think the most common sentiment. But like Devjit said, TensorFlow is getting much better. So I think a more modern API, which I'm not at all familiar with, is probably fairly good. That's also something that I've heard, but only heard. I've not looked into that too much. But
I mean, it makes sense if you want to do something like more research style. PyTorch makes more sense because like it looks like it's more flexible.
Yeah. That's what I feel as well. Okay, so now let's actually try to create a DNN and train it, right? So the first step towards any, okay, any questions or any more questions? Sorry if I felt like I jumped very quickly. So, okay, if there are no questions, then I'll go to this code here. So you can see this as well, right?
Yeah.
Yeah. Okay, so the first step towards any training process is to get the data. So what we're going to do here is going to train over this particular data set called MNIST. So MNIST, this was actually one of the original data sets that was used for, I think it was used in the first CNN paper, if I'm not wrong.
First, what paper?
The convolutional neural network paper.
No. Have we given it to them?
Yeah. This is available for download. Like it's actually a part of the, like it's part of this Torch Vision package itself. It's so much common right now that it's there. Like you can just download it very easily.
It's like a hello world for
yeah
deep
for
learning. So
yeah.
Okay.
So Devjit, it is the first CNN paper, or even before that, I don't remember.
which I think there were like more for MNIST, right? Yeah, that was the first CNN.
Right. I remember. Yeah.
So what is the neural net here that is being trained for this data set?
Yeah, so the neural net here is going to have this particular structure. It's going to have firstly
that you're creating later on. Okay?
Yeah, I'm going to create later on. So firstly, let's just look at how you download this data set and what this data set is, and then we'll go into the DNA. So the input size of this, these are basically pictures. So these are handwritten pictures of digits that are going to be classified. So there are going to be 10 classes that you want your neural net to predict. Sorry. The images are itself 28 by 28 pixels. Each pixel is just going to be black or white. So the images are black and white. So that basically gives you, for each input is going to be 28 times 28, right? So now getting this data set, okay, here. So this data set can be get as a part of the Torch Vision package if you want to get it from the like Torch, like PyTorch related things. There are also other like if you're using TensorFlow, then you can download it via their packages as well. There you can also get it very easily as like zip files online. Several places give it, but I've used this one. So inside the Torch Vision package, there is this datasets module, and inside the datasets module, you can get MNIST. So what this module will do is it will download MNIST for you. I already have it downloaded. So if I run it, it won't download it again, but you can basically download it and it will put it in this particular directory. So as you can see, there is this data directory, and inside data there is MNIST and so on. You can specify whether you want the training part of the data set or the testing part. They're like two separate sets of images. One was used for training and one testing in that original paper. So you can choose which one you want, or you can download both separately. what we're going to do is now we're going to take these data sets and apply two transforms on it. So this Torch Vision package also has this other module called transforms, which has a number of great utility transfers specifically for working with images, because Torch Vision is for image related machine learning stuff, machine vision essentially. So the two transforms that we're going to apply, the first one is just going to convert the image into a PyTorch tensor. So that transform is just going to convert the pixel values in whatever format they are into PyTorch tensors. And then the second one is going to normalize that. So the normalization is essentially, it'll shift it and scale it so that the distribution becomes of the pixels becomes a normal distribution with mean at 0 and standard deviation 1. So for that, you need to know what the mean and the standard deviation of your MNIST distribution is, which again, you can get these figures online and these are in the paper. But and any tutorial in search of will also give you these particular figures. But this is basically the mean of the standard distribution and the variance of the standard distribution. And then if you normalize it with respect to that, you will get something that where your pixel values mostly are between 0 and 1 or -1 and 1. So yeah, so this is going to basically give you your data set. And this data set object, as you can see, is going to be, this data set object has this type called PyTorch.dataset. So this has a type of torch.datasets.dataset. And this behaves exactly like a Python iterator. So you can call iter on it, and then you can call next on it, and it will give you the one particular data point. And every time you call next, it will give you one data point and so on. So you can, run a for loop over it directly, for example. So each data point is going to be an input and output pair. So let's just look at what these look like. We'll just run this and get these two print statements. So let's just run this. Okay, before that, let me just go back and comment out this part of the code since we don't want to run this. Okay. Right. So, okay, I think I need to, yeah. So the two print statements were just executed, and this is like the first image. There are 28 times 28 pixels here. These are with respect to, like, these are the various values representing the pixel value. As you can see, they are roughly between 0 and 1, although there is some 2 and so on over here. And this basically makes it so that the standard distribution is centered around 0 with standard deviation 1. So there can be high and low values, but if you normalize it, then it's easier for the model to learn the distribution. So this is one particular pixel, and I just wanted to look at what is the type of the thing that is being returned. So you have firstly you have a pair, right? So, or a tuple. The first thing inside that is this tensor, which represents this huge tensor representing the input image. And the other thing is 5. So this 5 is basically your correct output for this particular image. So apparently this particular image refers to a 5. So this is basically returning a paired input and output. And the output is basically 5 and input is whatever in this particular case. So we can also look at the shape of the input. So this second print statement is going to print out the shape. And the shape in this case, so shape basically means how many dimensions are there and what are the sizes of each dimension. So as you can see, it's 1, 20, 28, which means there's it's basically an array with 3 dimensions. The first dimension has length 1, the second has 28, the third is 20. And that's just because, it's one comes from basically there's one channel for this image, right? So just one black and white channel, and the image is itself 28 by 20. So the next thing that we can do is show some of these images. I won't go over the details of this code. This uses something called matplotlib, which you can look at the details of it if you want, but it's not really directly necessary for us here. This is just for some visualization that I have done. So yeah, so you can just it's going to just randomly take some images and show those images and the corresponding labels. So you can see what kind of a image they are. These are handwritten, and so you have they are imperfect and no two things are different. It's a fairly interesting data set to train on. So okay, now let's come to actually creating the DNN. Right. So the way you do that in PyTorch is you create a class which subclasses this particular nn.model class. So anything that can be trained, like any parameterized distribution, let's say, is going to be a subclass of nn.model, right? So inside this, what you need to specify inside this class is basically just one particular function, which is called this forward function. So the forward function, what it is going to do is it's going to take your input for this model, or in this case, this DNN's input, and it's supposed to return y. So remember, this entire theme of using PyTorch is that you only need to define what happens in the forward direction, and the backward direction is just going to be automatically handled when you do dot backwards, right? So similarly, when you're going to define the DNN or any kind of neural network, RNN, LSTM, convolutional network, whatever that you have, all you need to do is you need to define the forward direction. So when you define the forward direction here, it's going to basically take your x and compute your output y. So for that, remember, we need to, so what we need to do is we need to pass it through several layers, right? So let's say that let's fix a structure for DNN. Let's say that the input is going to be whatever the size of our image is. Then let's say that we'll have the next layer size is going to be 200, then 100, then 50, and then finally 10. So the final output 10 is going to basically represent how much the neural network expects each particular, or what probability the neural network gives each particular output to be, right? So each one of these layers is going to have its own set of parameters, right? So what basically you can do, or the way that PyTorch works is, or the style of PyTorch, let's say, is that you can take, PyTorch already gives you some models in NN, and you can take them and build your own model by using them, right? So what you can do is you can say that, okay, I'm going to have this linear layer. So as you can see, I've got 4 linear layers over here. And what I'm going to do is when I get the input X, I'm going to pass it through L0 and then R. R is going to be a ReLU layer. So pass it through L0 and then ReLU and then L1 and then ReLU, L2 and then ReLU and then L3 and then ReLU, right? And then give the output. So these linear layers are basically going to be, in some sense, objects that hold all the parameters with respect to that particular linear layer. And when you initialize it, it automatically initializes the parameters to some random value. And you also need to pass in the size of the input of the linear layer and the output of the linear layer. So for example, L0, the size of the input is going to be the input underscore size variable. This variable we had defined up here to be 20 times 20. This is the size of the images. So you're going to have the size of your input data. Then the next layer's input size is 200, or this layer's output size is 200. So you get 200. And then you go from 200 to 100, and then 100 to 50, and then finally from 50 to 10, right? So those are your 4 linear layers. And ReLU, you only need one ReLU, because ReLU doesn't store any parameter. You don't need to, say, define multiple instances of the ReLU layer. So you just can define one ReLU, and then inside your forward function, you pass all of these through. So these objects will hold their own parameters. So each one of these L0, L1, L2, L3 holds its set of weights and biases for that particular linear layer. And in turn, since your class is a subclass of model, and these themselves are also subclasses of model, what PyTorch automatically understands to be the case is that the set of parameters for your class is the combination of all of the parameters for your linear layers, right? So essentially what happens is that your class's set of parameters that you can train, or that you can adjust via training, is going to be the total set of all the parameters involved in all of these linear layers. And then when you take a particular input and then pass it through like this and give the output, what's going to happen is that it's going to pass through all the linear layers according to the particular weight. It will be modified and so on. And this entire thing will be stored in the compute graph. And then when you do backward, all of the gradients will be will get assigned to the particular dot grad values of the respective weights and biases inside these objects. And we'll see that, like, or not directly maybe, but we'll see how to use that when we write the actual training code. So is this in some sense clear? Or are there any specific questions that you have? It might be feel a little vague. Hopefully it will get more clear if I write the actual thing. So training code.
What does x.view do?
All right, yeah. So this, see, the x has this weird shape, right? 128. So we want to sort of, in some sense, flatten it to a single single dimensional vector, right? Because if you remember, the linear layer is going to take just a vector, not some matrix of 28 by 28, right? So just so that the dimension mismatch doesn't happen, we're flattening it, and this is what this does.
Yeah, sure.
You can look at the documentation for how exactly, like what this means specifically, but yeah, that's essentially what this is. So if there are no other questions, I'm going to go ahead and write the SGD code. Right. Okay. So let's pick the number of epochs. Let's say 10. Let me just okay. Now, one of the other great things that PyTorch gives you in terms of data is this data loader. So we talked about how we had to sort of, in some sense, keep shuffling this data and generating new data and so on, right? Like splitting into batches and then shuffle, and then split into batches and then shuffle. This entire process is basically automatically handled by this data loader. So the data loader, you just pass your original data set in, your batch size in, and whether you want to shuffle. And it will basically give you an iterator where you can, each element of that iterator is going to be one batch and the corresponding outputs of that batch. So what we can do essentially is we can do this. Right. So what this will do is essentially it will give you the input and the output pair for this particular thing. And so X is going to be all a bunch of images, and Y is going to be the corresponding bunch of correct outputs for that. And then what we want to do is we want to get the output of the neural network. So let's call that NY. Before that, we have the DNN class, so we want to create a particular instance of the neural network. So let's say DNN is just this. Right, and all we need to do is we need to apply DNN on X. So notice that X was essentially an array of inputs, right? But we didn't need to loop over that, and the reason for that is going to again be because if you remember NumPy, you could just broadcast, like if you had some particular broadcastable operation, you could just broadcast it across an array of elements, right? So if you had some function that operates on X, and you had an array of multiple values of X, broadcasting allowed you to just pass an array of X's to that function, and it would basically operate on each one of them individually, right? So the same thing is happening here. Although X is in some sense an array of images, well, image-like tensors, let's say, because of broadcasting, you can pass that as directly to the DNN, and all of these particular things is going to be broadcasted. So X is, say, X1, X2, X3. Then this X becomes the views of X1, X2, X3. This Y becomes what happens when X1, X2, X3 is passed to the first layer. And similarly, what happens to that when it passes to ReLU and so on. So all of this is going to get broadcasted, and you can do this directly. So is this clear for everyone? Hello? Say yes or no.
Yeah, it's clear.
Yeah. Okay. So the next thing that we want to do is we want to create a loss function. So let's take the cross entropy loss. The cross entropy loss is basically what I introduced as the negative log likelihood loss. Sometimes it's also called the cross entropy loss. In PyTorch, the negative log likelihood loss actually refers to something that is slightly different from the cross entropy loss. I don't think I'll have time to go into that, but you can read the documentation and hopefully it will be clear. But just know that cross entropy loss is exactly what we were doing in the NLL when we were talking about the in the slides essentially. So what we want to do is then, so again, the loss function, this is a class as you can see, but what this creates is creates a callable object. Just like DNN is a callable object, when you call DNN, the forward function gets called. Similarly, the loss function itself is also callable, and it will give you the final scalar, the loss scalar that you want. So let's call that L. And this is going to be, so loss function takes two things. It's going to take the target and it's going to take the output and it's going to take the target. So you want to take ny and y. It will calculate the scalar for you, right? So now realize that right now we have this L and this completes the forward direction of this entire thing, right? So now all we need to do is we need to do L dot backward. And since we have up until this point, we have specified exactly what the forward direction of everything is. So call the neural network and then call the loss on that. L dot backward will automatically go back and calculate the gradients for everything with respect to your loss. It's going to take into account summing over your inputs. It's going to take into account all the linear layers, all the ReLUs, everything. So all of that is automatically handled for you.
Where is the step size mentioned here?
So the step size is going to be still not mentioned over here, but it's going to be a parameter of the optimizer that we're going to use. So that's going to come. Yeah. So right now you have gradients. So L dot backward is going to fill up your dot grad parameters for all the dot grad members for all the parameters that you have. So now what you need to do is you need to take that, you need to do this step, right? So essentially with respect to the pseudocode where we are at this point. So we are done up until this point here. We have calculated the gradients. Now you need to do this step, which means you need to call optim step, right? So what we do essentially, as I said in the beginning of this class, this particular function, this entire thing is usually captured by an optimizer. And as I said, we're going to use the Adam optimizer, right? So let's create an instance of that. I think. So just let it get. Right. Right. And you can see just from the autocomplete prompt, there's like a bunch of optimizers there. In fact, maybe since I've opened the Google thing, we can go into this. So it goes into all of that. But this is this fairly large list of optimizers that you have. And each one of these is, its own specific paper with its own thing and so on. Yeah, sorry about that. So the optimizer is, or let's just write OPT is going to be optim Adam, right? So so let's go into the Adams thing, and as you can see here, you have several different parameters. Like LR is going to be the learning rate or the step size. Then you have a bunch of other parameters that you can tweak according to you, and it gives you the optimization algorithm over here in some sense. But so my experience is that usually default works. The one parameter that you can try changing is this LR. If you feel like you're not converging fast enough, then you increase it. If you feel like you're like you see that your loss values is going all over the place, that might be because you're overshooting, then you decrease it. But all of these other parameters, usually the default values seem to work best. If you want to change it, you'll have to go into the very nitty-gritty details of how exactly this Adam optimization algorithm works. And you can do that. You can go and read the paper and do that. But yeah, so I won't be going into those details right now. I don't think we have time for that. So right now we're just going to stick, like for this code, we're just going to stick to the standard things. So what we want to do is we want to do optimizer dot. So yeah, one of the things that you realize over here is it requires this. It requires the parameter. So how the optimizer works essentially is it's going to attach itself in some sense, or it's going to look over or handle a set of parameters, right? So you need to give the list of parameters to the optimizer. So in this case, it's going to be the parameters of the DNN. So it's going to be DNN dot parameters. So because your DNN is a subset of or subclass of NN dot model, automatically it will get this field called the params, which is going to be the list of all the parameters, which in this case is going to be a combination of all the parameters of your linear layer. And when you create your optimizer, you need to pass in this list of parameters. So the optimizer knows what parameters it needs to optimize. And remember, what all the optimizer is doing is this this step here. But in some sense, instead of passing this PRMS thing every time, what you're doing is you're just when you're creating the optimizer as an object, you're saying what PRMS it should be looking at. So yeah. So then all you need to do is you need to do opt.step. Sorry. So what this will do is this will go over all the parameters. Remember that after you've done L dot backwards, all of these parameters already have their dot grad values filled, right? So all of these parameters have some correct dot grad values filled in there. And then when you do opt.step, what happens is that the optimizer looks at the list of parameters, goes over all of them, looks at the particular dot grad values they have, and then does whatever equivalent to this that it needs to do. So you can always just think of your optimizer as doing in some conceptual sense something similar to this. But again, like I said, there are more details that are used for faster convergence and so on. So the optimizer is basically going to get both the data of the current value of the parameters and its gradient by just looking at the parameters and its dot grad values, like dot grad members. So now L dot backwards, or let's say that these three, like these two are the forward direction. This was the backward propagation. These three combined is your gradient calculation. So these three combined is this gradient calculation. And then this is going to be optim.step here. Right? So opt.step is the step taking that we were doing in the pseudocode. So this is your basic training loop. There is one other thing that you need to do, which is that you need to set your gradients to 0 at the end of everything, at the beginning of before you calculate the gradients. So you do that by saying optimizer.0 grad. So this will reset the gradient values from the previous iteration of the loop, and then you can do all of these. So yeah, so now let's try and run this and see what happens. Okay, it's going to show this. Let's close that. Sorry.
Gunther,
Yeah.
It's 4:50.
Yeah.
5 is okay. 5 should be a hard stop. So yeah.
Yeah. Okay. So I think we need to do something.
It should be DNN.self because the class name is DNN, right? Oh, I don't know.
Wait, DNN.self?
No, does not make sense.
Right. I don't think. I think it.
Oh, it should be just be DNN if I'm not wrong, right? Or itself.
Yeah, I think that is okay. I think the
Do you have a parameters thing here? I don't see anything in like this DNN module, right? A DNN class that like I don't see any DNN dot parameters.
no, yeah, but it should like
Have.
it's a NN.module has a parameters, right?
Oh, yes. Okay.
Yeah, I don't think I have too much time here as well, so I think I messed this up.
Try printing it just.
Yeah, no, I think DNN.parameters is fine. It's just there's some shape mismatch that's happening.
Oh, okay.
Inside.
I mean, one question I had is you're giving these params as, see, the parameter are the weights, correct?
Right.
Yeah, but they are structured as per some, layers and so on, right? So is there a, but here you're giving it as a but the.
Oh, no. So DN dot parameters only have the hyperparameters of this Adam optimal. So I don't think DN dot parameters will have the weights, right?
No, I think so. Okay, I can check that.
Yeah, check it.
No, I think DNN.parameters is definitely the weight size.
No, but is there a format in which it has to be done, or that is taken care of automatically because these parameters are arranged in a certain way, as a big matrix?
Yeah, so these parameters are arranged as this list of vectors.
Okay.
So I think they are taken care of.
That's taken care of in that.
Yeah. So that is all taken care of internally.
Okay. So.
Yeah. So I think what I'll do is I hopefully at least was able to give some of the overview of the code since we're out of time.
You could fix the code
and send it
and upload it, and you could kind of discuss it briefly next time. Beginning of next class. Yeah. Or
sure,
let them review it, and if they have any questions, they can ask.
Yeah.
Is that okay?
Yeah.
Yeah, sure.
Okay. Yeah, if you could stop sharing, unless you have any questions or you want to add anything. Yeah. Then you want to try something, or you want to end it?
No, I do want to end. I think we are already out of time, right?
Okay. So you have to stop sharing.
No, I was just waiting for someone to ask any questions if they have.
No, I think